Hello. All right. Welcome. Today is my birthday. I know y'all are excited.
Birthday.
I'm 39, like for real, 39.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Dr. Turner.
Happy birthday to you.
Thanks, guys.
Yeah,
Like,
I'm not 39.
yo, it's my last birthday. Just kidding.
Look out for next year.
Yeah.
It's a doozy.
Yeah. So it's cool. It's cool. Anyway, yeah, my daughter made me a cake, decorated it. Kind of looks like the cake from Sleeping Beauty, but it's fine.
Picture.
Yeah. So anyway, okay, concrete. We're finally into actually designing concrete. So go like that. And yeah. So the first little bit of this lecture was all about like just some stuff about where we put the reinforcement and all that. And then now we're going to actually do an example. It took me a minute. The example that I had originally was the one from the book, and it's a T-beam, and let's just start with like a regular rectangle. But first we can talk about how we do the design. If we know the dimensions, all we have to do is determine the area of steel. If we don't know the dimensions, then we have to develop the dimensions. But we're starting out with, let's say we already know the dimensions of our beam, and we just have to figure out the steel. So we know, oh no. That hasn't happened in a while.
Hey, real quick, did you see my email about my mistake on uploading my homework?
Yeah, that's
okay. Just want to be sure.
What the heck? Why is this being weird? In case you don't know, I'm writing like 6 inches away from where that's showing up. This usually fixes it. If not, I'll open and close it. Sorry, guys. It's all like set to go, and what's it called? There we go. That was weird. Okay, so if we know the dimensions, we know that our strength has to be greater than or equal to how much we need from our factored moment. And our equation for our strength, not incorporating any concrete or any compression steel, right, is D minus A over 2. And in this equation, we don't know our area of steel because we're going to design it, and depth of our stress block. But we do know that they're related. With equilibrium. And then, so if we want to start out, we're going to say that this D minus A over 2 is some factor J times D. This is just a place to get us started. For beams, JD varies between 0.87 and 0.91. And for slabs and T-beams with positive bending, it's about equal to 0.95. That's just estimating that moment arm. Okay, that's the moment arm for my force couple. And this is just a stepping off point for designing the area of steel. So if we know the beam dimensions and we want to know our area of steel, tensile reinforcement, I have my equation times JD has to be greater than or equal to my moment, factored moment. And if I solve for AS, so the procedure that we want to follow is, let's see, we know prime C, Fy, our beam width, and our beam height. And our factor of moment. We know how much we want to support. And we have our assumptions that our steel has yielded. And we can estimate our D. That was like D equals H minus 2.5 inches or 3.5 inches. So one layer or 2 layers. So then we just solve for AS using that equation. Mu over phi Fy times JD. And I guess you assume a JD as well. And then you're going to use 2 equations. You're going to use equilibrium to calculate the depth of your stress block A. So we have C equals T, 0.85 F prime C, AB equals AS Fy. So that's AS Fy. And that's the AS that you just solved for in step 3. And now you use your moment equation to solve for AS, the same one that you just used before. Fy, but now you can use that A. Instead of that JD, you actually have an A to put in there. And finally, just iterate to converge your area of steel required and its associated stress block depth. Once you have that, you actually need to select bars so that, or that meet how about MEET? The area of steel that you just calculated. Check that you met minimum requirements, AS min. Check that you meet minimum spacing, minimum max spacing requirements. And then finally, calculate CMN, which is what we just did for the last month and a half. So number 10 is what we've just been doing. So I summarized it into a single step. Yeah, and verify that it's greater than MU. Everybody good? Can only go by the people that I see that they're not writing, so. Okay, so let's do an example. It's a lot of writing, but it's not as much work. So here we need 250 kip feet. 60 KSI steel, 4,000 PSI concrete. We're gonna assume number 4 stirrups and normal cover, which is 1.5 inches. We're gonna design the tensile steel for this rectangular section. So I'm going to, right, I gotta assume that my steel has yielded. And that JD, that's where I'm starting. Is about, I don't know, 0.90. I don't know. This is just a regular beam, so. And let's see, my D, I'm assuming I'm gonna have a single layer, so D is H minus 2.5 inches. So 20 minus 2.5 inches is 17.5. So my starting point, AS is NU over phi. I'm also assuming tension control. So it's 0.9. Phi Fy times JD. So 250 feet times, well, I'm gonna want that in inches, 12 inches per foot. 0.9, 60 KSI, 0.9 times 17.5 inches. So that's my starting point for my area of steel. The associated stress block with that is that. So (16-inch wide beam. And then you make a little chart with my area of steel and A. If I use 3.53 inches square of steel, I have a depth of 3.89 inches. Now I'm going to use the equation AS equals mu over dfy d minus a over 2. And the same a equation, as fy 0.85 f prime c. So if I have an A of 3.89 inches, I use that first equation to calculate an AS. So I take 250 times 12 divided by 0.9 times 60 times 17.5 minus 3.89 over 2. And I get 3.57. So I'm not that far off already. If I use that A in the top in the second equation, .94 inches. If you keep going, and 250 times 12. I get 3.5. I mean, we're converging basically, because it doesn't even matter because we have to choose bars anyway. So I guess we chose a pretty good guess for our JD.
So there's not like a set value of AS that we have to get to?
No, just basically like when, right? Trying to see if I can get the same number twice in a row is really what I'm trying to do.
So when the iterations begin to not change your AS.
Converge, right, yeah.
That's when you know you're close.
All right, this just gave me the same answer, so. Little arrows aren't terribly great. I just got the same area in a row. I mean, granted, 3.57 is not that different than 3.5, but so that means it converged. It usually only takes a couple rounds. Sometimes it'll start off like way different, and then by the second or third, it's converged. So I use the first equation up here where I have an estimate for my JD. And I was like, it's probably like 0.9 times D rather than D minus A over 2, right? That JD just replaces the D minus A over 2. And then that gives me an estimate for my area of steel. I use that to calculate an associated depth of my stress block. And now I have a depth of my stress block. I can use this equation where I have D minus A over 2 instead of the JD. And you just keep using these over and over until you converge. And AS and A don't have to match, they just have to, right?
Stop changing.
Yeah.
I have a question. Why did you choose to use JD on the upper end of the range?
Because I liked 0.9 better than 0.8. It was a nicer number.
Yeah, I like round numbers. Okay.
I don't know. Because I was feeling lazy. Or than 0.89. It's just a guesstimate to get you started. So.
I thought you might have had some other knowledge that, like, oh, because it's like this, I'm going to choose the higher end of it.
Nah, just guess.
Okay.
So, yeah. Although I hope it doesn't look confusing using 2.9s. Kind of like the 2.85s gets confusing sometimes, but yeah. So we assume we've yielded. We selected some ratio of our D as a starting point, and then used the equilibrium equation and the how much strength of the moment equation to calculate an area of steel and its associated stress block depth to converge on, this is about how much steel we need, right? So we need about three and a half square inches of steel. 3.58 square inches of steel probably does not exist. So that's the next step, right? So you go look at, you can do this different ways. You can say, if I have 2 bars, what size they need to be if I have 3 bars, or you could make a little bars and their area of steel for 1 bar and number of bars if I use them. So like, a number 7 has an area of 0.6 square inches. So if I use number 7, 3.58 divided by 6, oopsies, 3.58 divided by 0.6, I need 6 number 7s. If I use a number 8, which has an area of 0.79, I'll need 4.5 bars. So 5, but yeah, you want to be efficient. If I use number 9s, which have an area of 1, I'll need 3.6 bars. I use a number 10, which has an area of 1.27. I'll need 2.8 bars. You can keep going with like a number 11 or a number 14. What's the number 11? 5, 6. 2.3. That's not really great. So I would probably choose 3 number 10s because it's the closest to a whole number. You could choose like 4 number 9s. You have to think about fit too. 6 number 7s, I don't know if they would fit in a single layer. You might have to go to double layers. And then you have all that to deal with.
Do you prefer to try to fit them into one layer?
Yeah. I mean, it's not
It would change our assumption, right? Because then we couldn't do
right. Well, yeah. I mean,
minus 2.5.
yeah. It's more paperwork, right? It's like, I mean, you're gonna have to find the centroid anyway, or you're gonna have to find D anyway. It's just now it's easier with one layer versus finding the centroid of a group. I don't know. So it doesn't. You can maybe number 7s are like easier to come by or something. I don't know. It's not an exact science. It's design. But I don't know. I would choose 3 number 10s.
So, but we're already given B and H. So, if we're specified that we need a cover of 1.5 inches, then we're kind of limited on how big of a bar or that how. You see what I'm saying?
Right.
Okay.
Yeah. Right. That's why that's like since you know your dimensions, then you're like, well, I can't jam a bunch in there without while meeting spacing requirements. So let's 3 or 4 is usually like a nice number in a layer, unless you have a super wide beam or something. 2 to 4 is usually what you put in a layer, but like on an exam, as long as you follow all the criteria, if you chose 6 number 7s, that's fine. If you want to make sure that you have to calculate spacing and you have to calculate the D. So let's choose 3 number 10s. So I'm going to check the spacing. All right, my area of steel for 3 number 10s is 3 times 1.27.
Sorry, I have another question.
Yeah.
So on number 11s, since it would be 2.3 bars, would you round down to 2, or would you still round up to 3?
I think you'd have to round up to 3, but it would be interesting to. I was trying to think about that. It would be interesting to see, because right, it's
Because you can't
right.
too much under reinforce.
Right. Oopsies. Right. Right. If you keep that greater than in there. Oopsies. Right. That AS that we just calculated, that 3.58 should be a minimum. Because it's based off of this equation. AS must be greater than or equal to mu over phi, Fy d minus a over 2. Doesn't mean you couldn't try it and see if it works, because you do want under reinforced as well. But yeah, generally that should be a minimum. I don't know. I could calculate that, but I'm not going to right now. So.
All the math rules, gosh.
Yeah, but your little alligator, right? I mean, yeah. So, Right, so we're gonna choose 3 number 10s. I'm gonna check the spacing, and this is where I feel like people struggled last year. So I'm gonna draw it. When in doubt, draw it. Right. So I have, let's see, my cover. On either side. That's to the outside of that stirrup. Then I have my stirrup, which is a number 4. So that's a 1/2 inch. And then here's where it gets weird for some people. We need this distance right here, which is the inside bend diameter. So this is the bend radius. Of a number 4. Or it could be 1/2 a radius of a number 10. Or 1/2 a radius, 1/2 a diameter or radius. No, I don't know what you're doing. So the bend diameter is on page 470. There it is. The bend diameter is, so we're looking at minimum inside bend diameter for stirrups, hooks, and tie, or hoops and ties. I'm talking about a 90-degree hook because this is down in the bottom. A number 4, and the diameter is 4 times the times the stirrup diameter. So the radius is 2 times the stirrup diameter. Again, it's on page 470. Two times the diameter of the stirrup, so that's an inch. Because it's a number 4, which is half an inch. Half of number 10 is 1.27 inches divided by 2, so that's obviously less than 1. So this is an inch right here. And that's just saying we want the longitudinal reinforcement flat on the bottom, not like somewhere up here, like nestled in. We want it so that they're all flat on the bottom in one line, because the one in the middle will be on that horizontal bottom.
Do they touch the stirrup? Are they laying on the stirrup?
Yeah, they're laying on the stirrup. The better picture, rather than my drawing, like this, right? To get it to be down, it needs to hit there. So that these 3 bars are all in a line. We have to take into account the bend diameter. Because if it was like that, then it might be up there to try to get the half of a number 10. So a little bit of visualization, but just generally it's half of a bend diameter to get to the centroid of the corner longitudinal bars. So then we have half a number 10 and half a number 10. And a full number 10 right here, which are 1.27 in diameter. And what we want to know is our spacing. We don't know that. We know what it has to be at a minimum. We know the whole thing overall is 16 inches, right? That's my beam width. So if I put 3 number 10s in there with number 4 hoops and normal cover, what is my spacing between those 3? Is what you're trying to calculate. So I've got 16 inches is my width. Let's see, I've got 2 covers, 1.5 inches. To stirrups. I'm going from the outside in. Let's see. To bend diameters that are an inch. And then half a number 7, or 10, sorry, half a number 10 and a number 10. 1.27 inches. And some spaces. So this is my cover. This is my stirrups. This is my inside bend radius. These are my number 10s. This is my humor. So then you just solve for your spacing. Right? So 16 minus cover minus my stirrups minus my radii minus my number 10s divided by 2, my spacing, I get 3.73 inches. Anybody else get that?
I got 4.095, but I don't have a good track record with calculators, so I'm probably wrong.
Well, I don't know.
I got 3.72, so,
Yeah, I got 3.73.
or I got 3.73 also.
Okay, good. Okay, Jonathan says he's only ever seen them tied right in the corner. And I mean, we're talking about like half an inch. They probably look like they're right in the corner. And maybe the bend diameter, I don't know.
I got 3.732.
You know, we're talking about 0.4 inches on either side, you know, half an
I
inch.
used the 0.635 for the bend radius instead of 1. Did I miss something? Why did you use 1?
Because if it was 0.635, we're gonna use the maximum because we want the longitudinal bars resting on the bottom, which is this on the other side looks a little bit better. Versus
So you take the maximum of that chart.
yeah,
Okay.
versus
That's
if
why
it
my
was
number was off there right there.
yeah, versus if it was the 0.63, these would be up on the sides a little bit. So they wouldn't be all on the line.
The 1.27 inches, Dr. Turner, is the width of the number 10 bar. I don't have my
Yeah,
CI book with me. Okay.
yeah. It's the width, it's the diameter and the area.
Okay. Yeah.
Oh, it's the same. Let's see. Number 10 bar diameter. So if I go and check my minimum spacing, should be on page 467. Minimum spacing of reinforcement, yeah. It needs to be the greater of 1 inch a bar diameter, which would be 1.27 or 4/3 of the diameter of the aggregate. I think I gave that. So one inch, that, but there's 1.7 inches, 4/3, the aggregate, which I probably gave us. God, I cannot aggregate. Oh, I didn't give it. Let's just say it's not going to matter. I think I gave it in the homework. But let's just say the diameter of the aggregate that you're using is 3/4 of an inch. So that would be an inch. Because 4/3 times 3/4 is equal. So your maximum spacing is, or your minimum spacing is 1.27 and 3.73 is greater than 1.27. That's what all of that was, to just check that. Anybody have any questions about checking the spacing? It's really just a geometry problem, and drawing it out helps often. Hopefully the colors maybe help too. As long as you're not colorblind, then I'm sorry. We also have to check that we've met minimum steel, which we probably have with 3.5 inches. There's ASM. Right. Square root F prime C over F prime. Or so 16 inches. Oh, we didn't calculate D. We go back to this little drawing, right? D is our height minus, we're assuming it's 3 number 10s in one layer, right? We're looking vertically, we have 1.5 inches, and then, right, on number 4, it's just 1/2 inch, and then just 1/2 bar diameter to get to the centroid. So D is our height minus cover minus, so diameter of the stirrup. Minus half of a number 10. So it's a 20-inch, right? 20 inches minus 1.5 inches for cover, minus a number 4, which is half an inch, minus half of a number 10, 1.26. I don't know, 365, if you want to, you don't like all your digits.
Dr. Turner, can you go back to that diagram for a second?
Yep. Yeah, sorry, I drew it and then I went quickly to the next thing. All right. This is going to here. So I think the bottom one. I forget which one. This is like 0.88. This one is. Which we meet easily with our 3.8 square inches. So anybody have any questions about that? So back in the beginning, like an hour ago, right? We estimated an area of steel, assuming some moment arm. We used that to calculate its associated stress block. Use these equations to converge on an area of steel. This one converged really quickly. Use that to select bars. We're like, let's do 3 number 10s. Checked our spacing to make sure we met minimum spacing requirements, which we did. Checked AS min, and we're good. So now comes what you just did for the last month and a half, is calculating the nominal capacity. So if you guys want to take a couple minutes and calculate that, I know the answer. So. 3 number 10s, and a 16. Yeah, we just calculated B. Yes, got it.
So do we need to find a new A since we have a new area of steel?
Yes. Yes. Now you're starting from where we started before. You have a design section.
Is there a reason you're making us do 5 of these for homework? It's gonna be like 6 hours.
After this, I'm going to tell you how you can do it more efficiently.
Yeah, I'll use that.
Jonathan, I just saw your comment. Yes, Excel is our secret weapon. It's like some of you are finished. It's also Aaron Flowers' birthday today too. We have the same birthday, which is funny. Yeah. Coincidentally. Probably, I don't know if that was a break of privacy, but it's just funny. So yeah, the secret weapon is Excel for your homework. I did it to I use Excel all the time when I can't find my calculator. I don't know if you guys do, but you can screenshot this. I'm not going to send it to you, but I put in right all my stuff, my F prime C, my FY, my this is where you can vary stuff, right? Your width and your height and your estimated stuff and how much capacity you need. And then this is calculating the area of steel and the A. That's what we did before. Here is, okay, if I need number, if I use these bars, this is the number. And then I'm like, I'm going to choose 3.81 inches squared. I actually checked the fit by finding I calculated the minimum spacing, which was 1.27 inches, and what my minimum beam width would be instead of calculating the spacing and check that it met it. Either way, it's fine because you need at least 10.83. We have a 16-inch wide beam, so probably yeah. By using if, I love Excel way too much. If statements. So there's my D. My A was 4.2 inches. I checked that I was yielding. Since it's only one layer, the strain in my steel is equal to the extreme tensile strain. It's greater than 0.005, and I got a FMN of 262 hip feet. So let's see. Write down A 4.2 inches, 0.007 something, 754, I don't know. Greater than Y, and 262 hip feet. Did everybody else get that number? So yeah, for the homework, this is what I would do, and it's actually on a different sheet of this Excel, is create this, however you want to make it, but so that all you have to do, because all you're varying is your height and your width and your let's see. I think it's your height, your width, and how much you need. And if you have this already, it'll calculate it for you. Right.
I thought that we were using A was 3.95. Did I miss something?
Did you use the one from earlier?
Mm-hmm.
Don't do that. That was assuming 3.58 inches.
Oh, the 3.81. Okay.
Yeah, so that's what I was saying. This page right here, calculate CMN as if this is your setup. We're starting from the very beginning, what we've been doing for the last month and a half.
Okay.
All the numbers before don't matter. That was to get to this point.
Okay.
So yeah, don't recalculate a new A, or don't reuse the A. Calculate a new one because you have a different area of steel. You don't have 3.58. You have 3.81. Or I think it's 3. If I keep saying the wrong numbers, it's the other one. But yeah, the numbers that we had before, you have to recalculate. It's kind of like when you go back and figure out that your steel hasn't yielded. Now you have to go back and change everything. Luckily, the steel yielded and everything was fine enough to do that. But yeah, this page right here is where we started all of our other problems. And let's see, the homework. So yeah, the homework is, oh no, it's all the same MU. It's just different widths and heights. That's right. I'll update it, but assume your aggregate is 3/4 of an inch so that it doesn't matter. I'll update that. Other than that, I think you have everything you need to know. Notice I put number 3 still, it's not number 4, so that's gonna change, but still a 1.5 inch cover. So yeah, for your homework, I would recommend making an Excel spreadsheet and like 5 different sheets or however many combinations you want. And that's due on Tuesday, but if you make the Excel, it should go really fast. So, does anybody have any other questions about this process? Next, we're gonna do unknown dimensions, so we have to determine everything, and then compression steel, and then we're done, and we'll move on to shear and then columns. So I'd like to get through both unknown dimensions and compression steel next week, but we'll see how it goes. Anyway, okay, if you guys don't have any more questions, this will be posted with the stuff. It's a notes on Blackboard, so. Yeah, I guess other than that, have a good afternoon, evening. Talk to y'all later. Bye.